A physicist who dedicated her entire career to debunking UFO conspiracies just admitted something that should send chills down your spine. Sabine Hosenfelder, the woman who has laughed at alien theories for decades, just publicly stated that we need to seriously consider the possibility that the interstellar object racing through our solar system right now might actually be alien technology. And Avi Loeb, the Harvard scientist everyone called crazy, might have been right all along. In just 13 days, 3I/Atlas reaches its closest point to the Sun. It will either break apart like any normal comet, or it will do something else entirely, something that could change everything we thought we knew about our place in the universe. But that's just the beginning of what's unfolding right before our eyes. A 12,000-year-old sphere discovered in Colombia responds to ancient Sanskrit chants. Congress just revealed footage of an unidentified aerial phenomenon surviving a direct hit from a Hellfire missile. NASA found potential biosignatures on Mars, and artificial intelligence just achieved something no human ever could. The next 60 days will either prove we are alone in a dead, silent universe, or reveal that we never were. Every scientist who dismissed this as impossible is about to be proven catastrophically wrong. If you're enjoying this deep dive into the mysteries unfolding right before our eyes, do me a favor and hit that like button right now. Subscribe to the channel so you don't miss what happens next, because understanding this content, really grasping what's at stake here, is absolutely crucial. These aren't just interesting stories. This is potentially the most important moment in human history unfolding in real time. Leave a comment telling me where you're listening from, what time it is there, and whether you think 3I/Atlas will break apart or reveal something extraordinary on October 29th. Your engagement helps this video reach more people who need to understand what's coming. Now, let me take you on a journey through one of the most extraordinary moments in scientific history. Let's talk about why one of the most rational, skeptical voices in physics just broke ranks with the entire scientific establishment. Sabine Hosenfelder isn't your typical scientist who chases headlines or sensational claims. She built her entire reputation systematically dismantling pseudoscience, tearing apart UFO claims with the precision of a neurosurgeon, explaining in excruciating detail why faster-than-light travel violates the laws of thermodynamics, why quantum consciousness theories are complete nonsense, and why every single grainy video of lights in the sky has a perfectly mundane, rational explanation. She's the scientist that other scientists point to when they want to shut down speculation and wild theories. She's the rational voice, the skeptic, the person who applies rigorous scientific thinking to every claim and finds the logical flaws that enthusiasts conveniently ignore. Which is exactly why her latest video about 3I/Atlas sent absolute shockwaves through both the scientific community and the UFO research world. She didn't just say the object is interesting. She didn't hedge her words with maybes and possiblies and we should investigate furthers. She looked directly into the camera and said, with full awareness of what she was saying, that we need to seriously consider that this could be alien technology. Coming from Sabine Hosenfelder, that statement carries the weight of a confession. It's like watching a career prosecutor who has sent hundreds of criminals to prison suddenly argue passionately for the defense. Something fundamental shifted in her analysis, and that shift tells us more than any individual data point ever could about what we're actually looking at. Let's be absolutely clear about what happened here, because this matters. Sabine reviewed the same scientific papers that every other astrophysicist in the world has access to. She looked at the trajectory data, analyzed the spectroscopic analysis, examined the emission patterns. She had access to exactly the same information as her colleagues. But where other scientists saw anomalies they could explain away with creative reasoning, where they saw oddities they could dismiss with hypothetical scenarios, she saw a pattern that made her deeply uncomfortable. Not uncomfortable because the data is bad or unreliable. Uncomfortable because the data is too good, too consistent, too deliberately strange to fit into comfortable categories that let us sleep soundly at night. The video opens with her characteristic dry humor, almost apologizing for what she's about to say. She knows exactly what this admission costs in academic circles. Suggesting alien technology isn't just controversial in the world of serious science, it's career suicide. It's professional annihilation. You become the person nobody wants to collaborate with. The researcher whose grant proposals get quietly shelved in filing cabinets and never spoken of again. The name that gets systematically removed from conference speaker lists. The scientist whose emails suddenly go unanswered and whose calls aren't returned. The stigma is real, it's brutal, and it's been deliberately cultivated over decades to keep scientists from asking certain questions or considering certain possibilities. And yet here she is, Sabine Hosenfelder, stepping deliberately into that minefield with full awareness of what it means for her career, her reputation, and her standing in the scientific community. Her argument centers on something that most people completely overlook when they think about scientific discovery and how science actually works in practice. We focus obsessively on type 2 errors, what statisticians call false positives, which means believing something that isn't actually true. Science has built enormous machinery around avoiding these kinds of mistakes. We have peer review processes, replication studies, statistical significance thresholds that must be met. The entire structure of modern scientific research is fundamentally designed around one principle: preventing us from being fooled by false patterns, by coincidences, by mistakes in observation or interpretation. But here's what Sabine points out with devastating clarity. We have almost no protection whatsoever against type 1 errors, what statisticians call false negatives, which means rejecting something that is actually true. Think about that distinction for a moment, really let it sink in. Science is asymmetrically cautious by design. It would rather miss 1,000 genuine discoveries than accidentally endorse a single false one. And that makes perfect sense for most scientific research. If you incorrectly claim that a new particle exists, other scientists will eventually figure out your mistake through replication attempts, and your reputation suffers, but no permanent harm is done to civilization. The scientific process is self-correcting over time. But what if the thing you're rejecting isn't a particle or a mathematical theory? What if it's evidence of intelligent life beyond Earth? What if it's a spacecraft from another civilization? The cost of a type 1 error in that scenario isn't just professional embarrassment or a retracted paper. It's potentially catastrophic for our species. If we dismiss alien technology because we're too afraid of being wrong, because the social cost of considering the possibility is too high, we might miss the single most important discovery in human history. We might fail to recognize a genuine threat to our civilization. We might ignore a once-in-a-lifetime opportunity for contact with an intelligence beyond our world. And unlike a failed particle physics experiment where you can run new tests and correct your mistake, you don't get a second chance with an interstellar visitor. The object passes through our solar system, we wave it goodbye, and we never know what we missed. The opportunity is gone forever. This is the absolute heart of Sabine's argument, and it's philosophically sophisticated in ways that casual observers might miss. She's not saying 3I/Atlas is definitely alien technology, and she's very careful about that distinction. What she's saying is that the cost-benefit analysis of scientific caution is completely backwards when it comes to interstellar objects. We should be investigating as if it could be artificial, not because we're certain it is, but because the stakes are simply too high to default to the comfortable, safe explanation that lets us avoid difficult questions. The risk of being wrong about investigating is tiny compared to the risk of being wrong about ignoring. But here's where Sabine's analysis gets truly interesting, where it moves from philosophy into hard science. She doesn't just make an abstract philosophical argument about risk assessment. She walks through the actual data point by point, systematically, and shows why this object is genuinely unprecedented in ways that should concern every scientist looking at the evidence. Not unprecedented in the vague sense that it's a little unusual or somewhat odd. Unprecedented in the precise sense that it breaks fundamental patterns we see in every single other comet and asteroid we've ever studied throughout the history of astronomy. Let me start with the emissions because this is where the strangeness becomes undeniable. 3I/Atlas is shedding nickel and iron at rates that the peer-reviewed scientific papers describe as exceptional. Not high, not unusual, exceptional. That's careful scientific language, deliberately chosen, for we have never seen anything remotely like this before, and we don't have any theoretical models that adequately explain what we're observing. Now, comets do shed material as they approach the sun and heat up. That's completely normal behavior that we've observed thousands of times. But the specific composition and the sheer quantity of what 3I/Atlas is emitting don't match any pattern we would expect from a natural icy body formed in the cold depths of interstellar space. Nickel and iron in these specific proportions and at these emission rates suggest something else entirely. Something that has been processed, something that has been refined, something that looks less like random cosmic debris and more like manufactured components experiencing thermal stress and degradation. Then there's the carbon dioxide to water ratio, which is even more bizarre when you understand what it means. Every comet we've ever studied, without exception, has a predictable, stable relationship between these two substances. Water ice dominates the composition, with carbon dioxide mixed in at relatively low, predictable concentrations. That's what comets do, it's definitional. 3I/Atlas completely flips that script in a way that shouldn't be possible through natural formation processes. It's pumping out carbon dioxide at roughly 8 times the rate of water vapor. That's not just unusual, it's fundamentally backwards from everything we understand about comet formation and composition. And here's where it gets really uncomfortable for scientists trying to maintain natural explanations. Some researchers noted very carefully in their published papers that this specific ratio could fit what you would theoretically expect from exhaust from some kind of propulsion system, from a spacecraft venting gas as it maneuvers through space. Sabine doesn't claim that's definitely what's happening, and she's appropriately cautious about that. But she points out the obvious logical issue that everyone's dancing around. When you see a ratio that looks like rocket exhaust, acts like rocket exhaust in terms of its spectroscopic signature, and appears in an object that's moving on an unusual, somewhat suspicious trajectory through our solar system, maybe, just maybe, you should seriously consider the possibility that it actually is exhaust from something artificial. The light polarization data adds yet another layer of genuine strangeness to this mystery. When sunlight reflects off an object in space, it creates a polarization pattern that tells us enormous amounts about the surface composition and structure of that object. We've developed sophisticated techniques for reading these patterns. Asteroids have characteristic polarization signatures. Comets have their own distinct signatures. We've observed literally thousands of these objects over decades, building up comprehensive databases of what normal looks like in precise quantitative terms. 3I/Atlas shows a polarization pattern that researchers described in peer-reviewed literature as unprecedented among asteroids and comets. Let that word sink in, unprecedented. That's not language scientists use lightly or casually in formal publications. It means the surface of 3I/Atlas is reflecting light in a manner that doesn't match any natural object we've ever observed in the history of astronomy. The pattern suggests a surface that is either incredibly smooth, far smoother than natural geological processes typically produce, or structured in specific ways that natural processes simply don't create through random chance and physical weathering. Think about the fundamental difference between a river rock that's been worn smooth by water flowing over it for centuries, shaped by random erosion and countless tiny impacts, versus a ball bearing that's been precisely machined to exact tolerances in a factory, deliberately crafted to achieve specific properties. Both objects are round, both appear smooth to casual observation, but they reflect light in fundamentally different ways because one is the product of random, chaotic natural erosion and the other is the result of deliberate, intentional engineering with specific goals and design parameters. The tail pointing toward the sun is perhaps the most visually striking anomaly, the one that even casual observers can understand represents something profoundly wrong. Comet tails point away from the sun, always without exception. It's one of the most basic, fundamental facts of observational astronomy, something we teach to children in elementary school. The solar wind, that constant stream of charged particles flowing outward from our star, pushes gas and dust away from the comet's nucleus, creating that characteristic beautiful streaming tail that always points in the opposite direction from the sun. It's physics, it's reliable, it's predictable. 3I/Atlas has a tail pointing toward the sun. Researchers describe this behavior, in carefully hedged scientific language, as not common and possibly observed for the first time in the history of modern astronomy. That level of extreme hedging in a scientific paper, all those qualifiers and cautious phrasings, translates pretty directly into plain English. We have absolutely no idea what physical mechanism is causing this, and according to our current understanding of physics and astronomy, it shouldn't be possible at all. Some scientists have suggested that perhaps unusual magnetic fields or highly asymmetric outgassing patterns could theoretically create this effect under very specific conditions. But those alternative explanations require stacking multiple unusual conditions together, conditions we've never actually observed in any other comet, conditions that seem specifically tailored to explain away this one uncomfortable observation. And here's the logical problem with that approach. You can explain absolutely anything if you're willing to invoke enough unusual, unobserved conditions and stack them together creatively. At some point, intellectual honesty requires asking whether the simplest explanation, the one that requires the fewest unobserved phenomena, might actually be that the object isn't behaving like a comet because it fundamentally isn't a comet at all. Sabine also carefully addresses the trajectory, though she's more cautious and measured here than with some of the other anomalies. 3I/Atlas is moving almost exactly in the plane of our solar system, staying within about 5 degrees of what we call the ecliptic, the flat disk where all the planets orbit. For a random interstellar object, an object that formed around another star and was ejected into the vast emptiness between stars, that specific alignment has roughly a 1 in 500 chance of happening purely by natural coincidence. That's not impossible, not even close, but it's improbable enough to notice, to raise an eyebrow, to add to the growing list of individually explainable but collectively suspicious features. Even more interesting when you dig into the orbital mechanics. The object makes close approaches to Mars, swings around toward Jupiter, and approaches Venus. 3 of the most significant planetary bodies in the inner solar system, 3 prime targets for scientific observation, while notably staying quite far from Earth throughout its entire passage. If you were designing a reconnaissance mission from scratch, if you were an alien civilization wanting to study our solar system while minimizing the risk of detection or interference, you might choose exactly this trajectory. Maximize observation opportunities of major planets with diverse characteristics, gather data on atmospheric composition and magnetic field structures and orbital mechanics, while staying well clear of the one planet that has active space infrastructure that might detect you, track you, or potentially interfere with your mission. Now, that's obviously speculation, and Sabine is careful to label it as such. But here's what makes it more than idle speculation. It's testable speculation based on falsifiable predictions. If 3I/Atlas were actually artificial, engineered by some intelligence, we should observe certain very specific behaviors as it reaches perihelion and comes under maximum thermal stress. We should see controlled, precise maneuvers rather than chaotic tumbling. We should see additional emissions that correspond to active systems rather than passive outgassing. We might possibly see detachment of smaller objects, probes or sensors separating from the main body. If it's natural, if all these anomalies are just a statistically unlikely combination of unusual but not impossible features, it should break apart under thermal stress or show typical cometary activity that we recognize from decades of observation. And here's the remarkable thing. We're about to find out which scenario actually plays out. This isn't theoretical. This is happening right now in real time as you listen to these words. The test is already underway. What makes Sabine's analysis so genuinely powerful, so intellectually compelling even to skeptics, is that she's not coming at this from a place of wanting to believe, of hoping for aliens, of seeking attention through sensational claims. She has spent literal years, much of her professional career, carefully and systematically explaining why alien hypotheses are almost always wrong when people propose them. She understands, probably better than most scientists, the overwhelming statistical probability that 3I/Atlas is exactly what the majority of her colleagues think it is. A strange but ultimately natural object, an unusual comet with properties we haven't observed before but that don't require revolutionary explanations. But she also understands something that many of her critics seem to miss. Being overwhelmingly likely isn't the same thing as being certain. Probability isn't certainty. And when we're talking about stakes this enormously high, when we're discussing potential evidence of non-human intelligence, of technology from another civilization, we simply cannot afford to let high probability calcify into unquestionable dogma that prevents us from looking at uncomfortable evidence. The scientific community's response to her video has been absolutely fascinating to watch unfold. Some colleagues, speaking privately and usually anonymously, quietly thanked her for saying publicly what they'd been thinking privately but couldn't say without destroying their own careers. Others dismissed her video as attention-seeking, a respected physicist sadly going off the rails for clicks and views, sacrificing her scientific credibility for YouTube fame. But the most interesting and telling responses came from researchers who work directly with the 3I/Atlas data, who have their hands on the actual observations. They didn't say she was wrong about the data. They didn't claim she was misinterpreting the observations. They said she was premature, that we need more observations, more analysis, more certainty before making any extraordinary claims about what we're seeing. And that brings us right back to Sabine's fundamental point about type 1 errors versus type 2 errors. How much certainty is enough? At what precise point does the entirely reasonable scientific demand for more data and better analysis become a psychological shield against uncomfortable conclusions we don't want to face? Sabine argues, persuasively I think, that the threshold for investigating something as potentially artificial should be dramatically lower than the threshold for publicly claiming it is artificial. Those are two very different standards, requiring different levels of evidence. Right now, at this moment, most of the scientific establishment treats those two thresholds as essentially identical. Unless you have proof beyond any shadow of doubt, absolute certainty that would convince the most hardcore skeptic, you don't even publicly mention the possibility that something might be artificial. You don't ask the question out loud where other people can hear you. That attitude might have made reasonable sense back when interstellar objects were purely theoretical curiosities, mathematical possibilities that we'd never actually observed. But we've now detected and studied 3 confirmed interstellar objects in less than a decade. They're not rare, exotic visitors. They're common. They pass through regularly. We were just blind to them until our detection capabilities improved enough to spot them. And if interstellar objects are actually common, if they pass through our solar system on a regular basis, and if some unknown but non-zero fraction of them could potentially be artificial rather than natural, then we're playing an incredibly dangerous game where the long-term cost of excessive skepticism, of refusing to investigate uncomfortable possibilities, might be catastrophically higher than the cost of investigating and being wrong. October 29th is now just 13 days away. That's when 3I/Atlas reaches perihelion, its point of closest approach to the Sun, when it will experience maximum thermal stress and radiation pressure. Every major telescope that can be brought to bear will be watching carefully. Ground-based observatories scattered across the planet, space telescopes free from atmospheric distortion, and most crucially ESA's JUICE spacecraft, which will have an unobstructed view and will gather unprecedented high-resolution data throughout November as the object emerges from behind the Sun from Earth's perspective. If the object behaves like a natural comet, it will likely fragment spectacularly or show dramatically increased outgassing as internal ices vaporize under solar heating. If it behaves like something else, like something that was designed and built rather than naturally formed, well, that's when things get genuinely interesting and potentially civilization-changing. Avi Loeb has been saying publicly for weeks now that November and December will be absolutely critical months for understanding what we're really dealing with. If 3I/Atlas survives perihelion completely intact, if it continues to show anomalous behavior that can't be explained by any natural model, then the natural comet hypothesis becomes exponentially harder to defend with a straight face. If it breaks apart spectacularly in a way consistent with a fragile icy body under thermal stress, then the skeptics will quite reasonably claim vindication and we can all return to our comfortable assumptions. Either way, we're about to get more comprehensive, higher quality data than we've had for any previous interstellar visitor in human history. But the real question that Sabine is ultimately asking, the deeper philosophical point beneath all the technical discussion about emission spectra and orbital mechanics, isn't really about what 3I/Atlas is. The real question is about what happens to science itself, to the entire scientific enterprise, when we become too afraid to consider uncomfortable possibilities that threaten our worldview. What happens when the social cost of being wrong about aliens becomes so overwhelmingly high that we would collectively rather risk missing first contact with another civilization than risk looking foolish to our peers? That's not science anymore. That's not rational inquiry. That's conformity dressed up in equations and wrapped in the language of rigor. Sabine Hosenfelder just risked her professional reputation, her career trajectory, her standing in the community she's worked her entire life to be part of, to say that maybe, just maybe, we should look at this object with genuinely open eyes instead of eyes that are closed by fear of social consequences. The fact that such a statement requires courage, that it's professionally dangerous to even suggest we should investigate, tells you absolutely everything you need to know about the current state of the scientific field when it comes to anything touching on potential extraterrestrial intelligence. And the fact that she felt compelled to make that statement anyway, knowing full well what it might cost her, tells you how seriously she takes the data she's seen. She's not doing this lightly. She's not seeking attention. She's genuinely concerned that we might be missing something of staggering importance because we're afraid to look directly at it. In 13 days, we'll start getting answers to at least some of these questions. But the bigger question that Sabine has raised transcends this one object, this one moment. It's about whether science as an institution, as a social system, can adapt quickly enough to handle the possibility that we might not be alone in the universe, and whether we can manage that adaptation before it's too late to matter, before opportunities slip through our fingers because we were too timid to grasp them when they appeared. Now, let me take you deeper into what Sabine actually saw in those scientific papers, what specific data points were so compelling that a physicist who built her entire career on debunking extraordinary claims suddenly said we need to take the extraordinary claims seriously. Let's dig into the real details, the hard science, because the devil here isn't just in the details, it's in the pattern of details, in how they connect and reinforce each other in ways that become increasingly difficult to explain away. Any single strange measurement taken in isolation could potentially be an instrument error, a calibration issue that nobody caught, a misinterpretation of ambiguous data. That happens in science. Instruments malfunction, software has bugs, human beings make mistakes in analysis. But when you systematically stack 5 or 6 genuinely impossible things on top of each other, all appearing in the exact same object, all confirmed by multiple independent observations, you start rapidly running out of mundane explanations that can account for everything simultaneously. The nickel emissions deserve far more attention than they've gotten in popular coverage of the story. When the research team described them as exceptional in their peer-reviewed paper, they weren't being dramatic or engaging in hyperbole for effect. They ran the spectroscopic analysis multiple times with different instruments, carefully checked all their equipment for calibration errors, compared their readings against every known comet signature in comprehensive databases built over decades. Nickel simply shouldn't be present in these quantities in a natural comet, not even close. There's no formation model that predicts it. Think carefully about what a comet is actually supposed to be at the most fundamental level. It's often called a dirty snowball, and that's reasonably accurate. Water ice dominates, mixed thoroughly with dust particles, some carbon-based compounds, maybe trace amounts of metals embedded in the structure. The metals are there, but they're locked up tight in mineral grains, tiny particles distributed throughout the ice matrix. As the comet heats up approaching the sun, the ice sublimates, turns directly from solid to gas without passing through liquid phase, and that expanding gas carries the dust particles away. You get a little bit of metal showing up in the emission spectrum, but it's minimal trace amounts that barely register. 3I/Atlas isn't doing anything remotely like that normal process. It's emitting nickel as if the metal itself is somehow vaporizing directly, as if there's so much concentrated heat and such unusual concentrations of pure metal that the nickel is turning directly from solid to gas. That requires temperatures we simply don't observe in normal cometary activity. It also requires the nickel to be present in specific chemical forms that can vaporize easily under those conditions, which is extremely unusual. In nature, throughout the universe, nickel is almost always bound up in silicate minerals or in iron-nickel alloys, the kind of mixtures you find in metallic meteorites. To get relatively pure nickel vaporizing off a surface in the quantities we're observing, You would need either industrial refining processes that concentrate and purify the metal, or you would need a thermal environment so extreme, so far outside normal parameters, that it's melting the object from within in ways that natural solar heating can't explain. Neither of those scenarios fits comfortably with a natural comet that formed in interstellar space. But both of them fit reasonably well with something artificial, with a spacecraft that has nickel components experiencing unexpected thermal stress, or perhaps with some kind of power system or propulsion system that uses nickel in its operation, maybe as radiation shielding or as structural elements in high-temperature environments. And here's what makes it even stranger and harder to explain naturally. Iron is also present in the emissions, but in different ratios than you would ever find in natural iron-nickel alloys formed by cosmic processes. It's as if someone deliberately selected specific metals for specific engineering purposes rather than getting the random, statistically predictable mixture that nature provides through stellar nucleosynthesis and planetary formation. Now combine that nickel anomaly with the carbon dioxide problem, which somehow manages to be even more bizarre when you understand the underlying chemistry. That 8-to-1 ratio of carbon dioxide to water vapor isn't just unusual or unexpected. It's thermodynamically strange in ways that violate our basic understanding of how comets form and what they should contain. Water ice is significantly more stable than carbon dioxide ice across a wide range of temperatures and pressures. In any natural comet forming in the cold depths of interstellar space, far from any star's heat, water should absolutely dominate the composition. That's not speculation, it's basic physics and chemistry. You can create carbon dioxide-rich comets under very specific, unusual conditions if the formation environment is extremely cold enough that carbon dioxide condenses and freezes before water gets a chance to dominate. But those rare comets should also be proportionally rich in other volatile ices like methane and ammonia, because those compounds condense under similar conditions. 3I/Atlas isn't showing elevated levels of those other expected compounds. Just carbon dioxide, massively out of proportion to everything else in ways that don't fit any known formation scenario. And here's where multiple researchers have pointed out something that makes everyone uncomfortable. This specific emission profile, this particular ratio and composition, looks remarkably similar to what you'd expect from chemical propulsion exhaust. Not identical, not a perfect match, but similar enough to raise serious questions. Carbon dioxide is a common, expected byproduct of hydrocarbon combustion. If you were burning hydrocarbon-based fuels for propulsion, you would absolutely expect to see water vapor and carbon dioxide in the exhaust stream, with the exact ratio depending critically on the efficiency of the combustion process and the specific chemical composition of the fuel you're burning. An 8-to-1 carbon dioxide to water ratio would suggest either a very carbon-rich fuel source or a very hot, very efficient combustion process that favors carbon dioxide production. Again, that's obviously speculation, we can't definitively prove it. But it's testable, falsifiable speculation based on the actual data we have rather than wishful thinking or science fiction. The alternative natural explanation requires us to believe a remarkable series of coincidences. We have to believe that 3I/Atlas formed under conditions that are vanishingly rare in the universe. That it somehow perfectly preserved those unusual conditions for billions of years while traveling through the radiation-filled environment of interstellar space. That it just happened to end up on a very specific trajectory that brings it through our solar system at exactly the historical moment when humanity has finally developed the technological capability to detect it and analyze it in detail. And that all of these low-probability events just happen to align by pure chance. Is that possible? Absolutely, yes. Is it probable? That's where the fascinating debate exists, where reasonable scientists can examine the same data and reach different conclusions based on how they weight prior probabilities and assess the strength of evidence. The light polarization data is where things transition from merely unusual to genuinely deeply weird in ways that have no comfortable natural explanation. Polarization is one of those fundamental properties of light that sounds somewhat abstract when you first encounter it, but it tells you absolutely enormous amounts about physical surfaces when you know how to read the signal properly. When unpolarized sunlight hits an object in space, the way that light reflects and scatters depends intimately on the surface texture at multiple scales, the chemical composition, and the structural organization. Rough, irregular surfaces scatter light chaotically in all directions, creating low polarization in the reflected light. Smooth, regular surfaces create higher, more organized polarization because the light bounces off at more predictable, consistent angles. Metallic surfaces behave optically differently than rocky surfaces. Icy surfaces have their own distinctive signatures. After decades of systematically observing comets and asteroids, building up enormous databases, astronomers have developed comprehensive libraries of what normal polarization patterns look like for different types of objects. You can often identify the general composition of an object, distinguish ice from rock from metal, just from its polarization signature alone, without ever needing to analyze its light spectrum through spectroscopy. It's an incredibly powerful diagnostic tool, which is exactly why the 3I/Atlas polarization data are so deeply troubling to everyone who's looked at them carefully. The object is producing a polarization pattern that doesn't fit any established category in our databases. It's not behaving like bare rock. It's not behaving like water ice or carbon dioxide ice. It's not behaving like a dusty mixture of rock and ice particles. The pattern strongly suggests an extremely smooth, highly reflective surface, smoother than natural geological processes typically create. But here's the problem that nobody can resolve. The spectroscopic data, the analysis of which wavelengths of light are absorbed and reflected, says the surface composition should not produce that kind of smoothness at all. Those two independent pieces of information are directly contradicting each other, and nobody has developed a good explanation for why that should be. One theoretical possibility is that the surface has a very thin, extremely uniform coating of some material that dominates the polarization signature while the underlying bulk composition shows up in the spectrum. That can happen naturally through a few processes. Frost can form a uniform layer. Very fine dust can settle uniformly across an entire surface under certain conditions. But 3I/Atlas is actively, continuously venting gas and shedding material in all directions. Any frost layer should be constantly disrupted by that activity. Any dust coating should be highly uneven, patchy, with obvious variations. Unless somehow the coating is being actively maintained despite the outgassing and particle ejection. Unless something is continuously creating and recreating that smooth surface through active processes. That sounds like science fiction, like the kind of thing you'd see in a movie. But we should remember that many things sounded impossible, like pure fiction, until we actually observed them happening. Ice geysers erupting from Saturn's moon Enceladus sounded absurd until Cassini photographed them. The idea of complex organic molecules in Titan's atmosphere was dismissed as unlikely until we found them. Liquid water currently flowing on Mars was considered impossible by many scientists until the evidence became undeniable. Sometimes the universe does things that sound completely impossible until we actually observe them happening, and then we have to rapidly update our models of what's possible. The tail pointing toward the sun is probably the single most visually dramatic anomaly, the easiest one to explain to non-scientists, and it has generated some of the most creative, elaborate attempts at alternative explanations I've seen in recent scientific literature. Some researchers have suggested that perhaps the object is rotating in some very unusual way such that outgassing jets are creating thrust vectors that push material forward instead of backward relative to the sun. That's theoretically possible, but those jets would need to be incredibly powerful, far more powerful than anything we've observed in natural comets, and precisely oriented in very specific directions to create the observed effect. Other scientists have proposed magnetic field effects, scenarios where the object's own magnetic field or complex interactions with the solar wind's magnetic field creates unusual particle trajectories that don't follow the normal pattern. Also theoretically possible, but we've never observed magnetic effects anywhere close to that strong in any comet we've studied. Comets generally don't have significant magnetic fields because they're made of ice and dust, neither of which is magnetic. The fundamental problem with all these creative alternative explanations is that they require multiple unusual, individually rare conditions to occur simultaneously in the same object. Yes, you could theoretically have very asymmetric outgassing from a weirdly shaped nucleus. Yes, you could theoretically have unexpected magnetic field effects from unusual composition. Yes, you could theoretically have unusual rotation states that create odd thrust vectors. But getting all three phenomena occurring simultaneously, and in exactly the right configuration to produce a forward-pointing tail while also simultaneously explaining all the other anomalies we've discussed, the probability space starts getting extremely uncomfortably narrow. Here's another way to think about this that makes the strangeness more intuitive. If you were an engineer designing a spacecraft that needed to efficiently vent excess heat from onboard systems, or needed to continuously expel reaction mass from some propulsion system, where would you point the exhaust? Would you point it backward, away from your direction of travel? Probably not, because basic physics tells you that would create thrust in the wrong direction, constantly slowing you down, wasting energy fighting your own exhaust. You would almost certainly vent forward, perpendicular to your travel direction, or to the sides. Anywhere that doesn't create significant unintentional deceleration that wastes your energy budget. A forward-facing plume of gas from such a system would look exactly like what we're actually observing with 3I/Atlas. It would appear as a tail pointing toward the sun because of the object's position and motion relative to our observation point. The trajectory analysis is perhaps the single most contentious point in this entire debate, because it involves extensive statistical arguments and probability calculations, and we all know that statistics can be manipulated, sometimes subtly, to support almost any conclusion if you're not extremely careful about your assumptions and methods. Yes, it's true that 3I/Atlas is moving almost exactly in the ecliptic plane, that flat disk where all our planets orbit. Yes, it's statistically unlikely for a random interstellar object to enter our solar system at that particular angle. Avi Loeb calculated, using straightforward geometry and probability, that the odds of a random object entering at that specific inclination are roughly 1 in 500. Not impossible, but unlikely enough to notice. Critics immediately and reasonably pointed out that we've only observed 3 confirmed interstellar objects total, so having one of them show an unusual trajectory is not surprising at all. With such a small sample size, unlikely things happen. Fair point, that's good statistical reasoning. But then you have to factor in the close approaches to multiple major planets in ways that maximize scientific observation opportunities. 3I/Atlas passes relatively near Mars, gathering data on its thin atmosphere and surface. Swings around toward Jupiter, the largest planet, the one with the most complex magnetic field. Approaches Venus with its extreme greenhouse atmosphere. All major targets of enormous scientific interest, all places where you would absolutely want to gather comprehensive data if you were systematically surveying our solar system's planetary diversity. The counterargument that skeptics immediately raise is obvious. If this were actually a deliberately planned reconnaissance mission by an intelligent civilization, why would it avoid Earth so carefully? We're the only planet with clearly detectable technosignatures, the only place where intelligent technological life is obviously, undeniably present. If aliens wanted to observe humanity, to study us, they would come closer. They would want detailed observations. Unless they don't want to observe us. Unless they're specifically not interested in humanity. Unless Earth is deliberately excluded from the mission profile for reasons we don't understand. Maybe the scientific goals are studying planetary formation processes, atmospheric composition and evolution, magnetic field interactions with stellar wind, phenomena that are better observed from a safe distance without the noise and complexity introduced by an active technological civilization that might detect you, might track you, might even attempt to interfere with your mission. Or maybe, just maybe, the trajectory is simply a coincidence. Maybe we're pattern matching, doing what human brains evolved to do, seeing intention and design where there's actually only chaos and random chance. That's the default scientific position, the conservative interpretation, and it's usually correct when we examine supposedly mysterious phenomena. Usually, but not always. What makes all of this so frustrating for everyone involved is that we could get definitive answers with better observations, with more resources, with bolder decisions. We could send an interception probe to 3I/Atlas. We have the technological capability, the delta-v requirements, the change in velocity needed, are high but absolutely not impossible with current propulsion technology. We could get close-up images with resolution that would show surface details. We could do direct compositional analysis with instruments in close proximity. We could measure magnetic fields, thermal emission patterns, all the data we would need to definitively distinguish between a natural object and something artificial. But we're not going to do it. Not because it's technically impossible or even extraordinarily difficult. Because it's politically and financially impossible in our current institutional framework. Nobody, no space agency, no government, wants to be the organization that spent billions of dollars chasing what ultimately turns out to be just a weird space rock. The risk of looking foolish, of having that failure prominently featured in political attacks and budget hearings for decades to come, is too high for any individual decision-maker to accept. So instead we watch from a distance, squinting at pixels on screens, arguing endlessly about spectral lines and statistical significance. We collect data that's just ambiguous enough to support multiple competing interpretations, and we wait passively for the object to leave our solar system, taking all its secrets with it into the vast darkness between stars, never to be seen again. October 29th is when 3I/Atlas reaches perihelion, when it comes closest to the Sun. That's when the object will be under absolutely maximum thermal stress from intense solar radiation. If it's a natural comet, that stress should cause dramatic, visible changes. Fragmentation as internal structure fails. Massively increased outgassing as deeply buried ices suddenly vaporize. Possibly even complete catastrophic breakup if the structural integrity is poor. If it's something else, if it's engineered, it might show very different behaviors. Controlled venting that starts and stops in organized patterns. Possible trajectory adjustments using that venting for propulsion. Stable configuration maintained despite the incredible heat and radiation, because it was designed to handle those conditions. We will be watching with every instrument we can bring to bear. ESA's JUICE spacecraft will observe the object continuously throughout November as it moves away from the Sun and back out toward interstellar space. Those observations will be absolutely crucial because they capture 3I/Atlas in its most active state, when whatever is causing these anomalies should be most pronounced and easiest to detect and characterize. The data won't be released immediately to the public. That's not how science works. It will take weeks or months to carefully process, thoroughly analyze, check for errors, and prepare for peer-reviewed publication. By the time we actually see the results, by the time papers are published and press releases are written, the object will already be far out into the outer solar system on its way back to interstellar space. But the real test, the real question that will determine how this story unfolds, isn't just what we observe in November. The real test is what the scientific community chooses to do with those observations. If the anomalies persist, if the object continues to behave in ways that don't fit any natural models, will researchers seriously consider and investigate artificial origins, or will they invent increasingly elaborate, increasingly contrived natural explanations to avoid the uncomfortable conclusion that challenges everything? Sabine Hosenfelder is essentially betting her reputation that the data will force the conversation forward whether scientists want it or not. She's betting that the anomalies are real, that they're persistent, and that they're ultimately unexplainable without invoking something beyond our conventional understanding of astrophysics. She might absolutely be wrong. The object might fragment spectacularly at perihelion and reveal itself to be exactly what most scientists currently think it is, an unusual but ultimately natural comet. But if she's right, if 3I/Atlas makes it through perihelion completely intact and keeps doing these impossible things that violate our models, then we're going to have a very different conversation in December than we're having now in October. And that conversation won't be just about this one object, this one mysterious visitor. It will be about how we approach the entire question of alien technology, how we balance healthy skepticism with necessary openness, how we handle discoveries that challenge fundamental assumptions about our place in the universe and whether we're alone. It will force us to confront whether science as an institution can evolve fast enough to deal with a reality that might be considerably stranger than we ever imagined, stranger than our current frameworks can comfortably accommodate. Because here's the thing that keeps serious researchers awake at night, staring at the ceiling, contemplating implications. 3I/Atlas is not unique. It's not a one-time anomaly. It's the third confirmed interstellar object we've detected and studied. We only developed the capability to routinely spot these objects within the last decade. How many more are passing through right now that we're missing because they're too small, too dark, approaching from unfavorable angles? How many passed through before we had the technology to spot them through all of human history? How many will come after? And if even a small percentage of them, even 1% or 1/10 of 1%, are artificial rather than natural, what does that mean for humanity's future? Before we go further, I want to make sure you're still with me, still engaged with this incredible story. If you've made it this far, if you're genuinely interested in understanding what might be the most important moment in human history unfolding right now, do me a favor. Hit that like button if you haven't already. It genuinely helps this video reach more people who need to understand what's happening. Make sure you're subscribed to the channel, because the next 60 days are going to be absolutely crucial, and you'll want to see the updates as events unfold. And drop a comment right now telling me what you think. Will 3I/Atlas fragment at perihelion like a normal comet, or will it survive and reveal something that changes everything? I read every comment and I'm genuinely curious what you think is about to happen. Now let's talk about someone who has been absolutely vindicated by recent events in ways that must feel surreal. Avi Loeb has been called many things over the past 8 years, and most of them haven't been complimentary. Attention seeker, pseudoscientist, the alien guy, Harvard's embarrassment. When he first suggested back in 2017 that Oumuamua, the first confirmed interstellar object, might potentially be artificial technology rather than a natural space rock, the backlash from the scientific community was absolutely swift and brutal. Now, with 3I/Atlas displaying behaviors that make Oumuamua look positively ordinary and conventional by comparison, that same establishment is starting to use language that sounds suspiciously, uncomfortably similar to what Loeb was saying all the way back in 2017. Unprecedented, exceptional, difficult to explain with conventional models, challenging our understanding. They're not calling it alien technology yet, they're still carefully avoiding that specific phrase, but they're systematically running out of conventional explanations that can account for all the observations simultaneously, and Avi Loeb is not being quiet about the vindication. His response to the 3I/Atlas data has been characteristically bold, uncompromising, and direct. Within days of the initial discovery announcement, he published a paper with co-authors Adam Hibbard and Adam Crowell asking the question directly, without hedging or diplomatic softening. Is the interstellar object 3I/Atlas alien technology? Not could it be, not might it possibly be under certain conditions, but is it? That framing alone, that directness, was enough to generate immediate controversy and pushback. You're not supposed to ask that question so bluntly in a peer-reviewed scientific paper unless you already have absolutely definitive proof that would convince even the most hardcore skeptic. But Loeb argues forcefully that this conventional wisdom is exactly backwards, that it gets the scientific method fundamentally wrong. You should ask the question as soon as you have sufficient reason to investigate seriously, not after you already know the answer with certainty. Science is supposed to be about asking questions and testing hypotheses, not about knowing answers before you're allowed to ask questions. The paper itself is genuinely fascinating because it doesn't just speculate wildly or make dramatic claims without backing them up. It systematically lays out specific, testable criteria for distinguishing natural objects from artificial ones, then methodically evaluates 3I/Atlas against those criteria using actual observational data and rigorous mathematical analysis. The results are deeply uncomfortable for anyone committed to maintaining the natural origin hypothesis at all costs. Start with non-gravitational acceleration, which is one of the clearest signatures of something unusual happening. Natural objects in space follow beautifully predictable paths determined entirely by gravity and their initial velocity vector. If you observe an object long enough, measure its position precisely enough, you can calculate its future trajectory with extraordinary precision using nothing but Newtonian mechanics. 3I/Atlas is not following the calculated gravitational path. It's showing small but statistically significant, measurable deviations that strongly suggest some form of non-gravitational acceleration is occurring. Now, comets can absolutely do this through completely natural processes, and we've observed it many times. Outgassing creates thrust through a basic rocket effect. As ice vaporizes and jets of gas shoot violently off the surface in specific directions, they push the comet slightly off its purely gravitational course through simple conservation of momentum. We've observed this effect in dozens of comets throughout the solar system. We can model it mathematically. We understand the physics thoroughly. But here's the critical problem. The acceleration profile of 3I/Atlas doesn't match the observed outgassing pattern at all. The thrust appears far more consistent, far more directional, far more controlled than you would ever expect from random jets of vaporizing ice erupting chaotically from a tumbling, irregular natural body. Loeb calculated carefully that if the acceleration continues at current observed rates, the object will be moving approximately 0.00006 astronomical units per day squared faster than gravity alone would predict. That's an incredibly tiny number. That's well within the margin of error for our observations and instruments. But it's also precisely what you would expect from a spacecraft making small, periodic trajectory adjustments to maintain a specific desired course through the solar system, making tiny corrections to compensate for gravitational perturbations and stay on target. Critics immediately pointed out, quite reasonably, that Comet 2I/Borisov, the second confirmed interstellar object, also showed clear non-gravitational acceleration. So clearly this is just normal, expected cometary behavior, and Loeb is making mountains out of statistical noise, seeing patterns that aren't really there. That's a fair point that deserves serious consideration. Except 2I/Borisov showed absolutely all the other definitive signs of being a completely normal, natural comet. It had a massive, obvious coma of gas and dust. It had a clear, well-defined dust trail. Its spectroscopic signatures matched known comets from our own solar system almost perfectly. It looked like a comet, it acted like a comet in every observable way, and when researchers calculated the expected acceleration it should be experiencing from the observed outgassing, the numbers matched the observations beautifully. 3I/Atlas doesn't match that pattern at all. The non-gravitational acceleration is clearly there in the astrometric data, but the amount of outgassing that should explain and account for it simply isn't sufficient. The numbers don't add up. There's a missing source of thrust that the visible activity can't explain. Then there's the question that Loeb keeps asking repeatedly, the question that nobody in the mainstream scientific community wants to answer directly or even acknowledge. If 3I/Atlas is just an unusual but ultimately natural comet, why is it timing its closest approach to the Sun to coincide precisely with the moment when Earth is on the opposite side of our star? October 29th isn't random chance. It's not a meaningless coincidence. It's exactly timed so that when the object is at its absolute brightest, when it's under maximum thermal stress from intense solar radiation, when whatever mechanisms are causing these anomalies should be most obvious and most easily observable, we simply cannot observe it directly from Earth at all. We have to rely entirely on spacecraft that aren't positioned on or near Earth. We have to wait patiently for the object to emerge from behind the Sun's glare before we can get good ground-based observations again from our major telescopes. Loeb suggests, provocatively but logically, that this could be absolutely intentional, deliberately planned. If you wanted to conduct operations near the Sun while minimizing detailed observation from Earth, from the one planet in this system with active space infrastructure and technological capability, this is precisely how you would time your approach. Position yourself strategically so that the Sun physically blocks direct observation from the planet with all the telescopes and tracking stations. Do whatever you need to do, whatever your mission requires, while hidden behind 200 solar radii of burning plasma that blocks electromagnetic radiation. Then continue calmly on your way, exit the inner solar system, before anyone gets a truly clear, unobstructed look at what you're actually doing. That sounds paranoid when you first hear it. It sounds like conspiracy thinking, like the kind of reasoning that sees patterns and intentions everywhere. But Loeb backs it up with actual probability calculations using straightforward statistics. What are the actual odds that a completely random object would just happen to time its perihelion passage to coincide so precisely with Earth being on the far side of the Sun from that perihelion point? It's not impossible, probability isn't zero, but it's low enough that you notice it, that you add it to the growing list of individually explainable but collectively suspicious coincidences. Add that timing to all the other low probability features of this object we've discussed, and the cumulative odds, the probability of all of them occurring together by pure chance, starts looking increasingly uncomfortably suspicious to anyone doing the math honestly. His most controversial claim, the one that gets him dismissed most quickly by mainstream scientists, involves what's called the dark forest hypothesis. This is an idea that originates from science fiction, specifically from Liu Cixin's remarkable novel The Three-Body Problem, but it's based on game theory that actual scientists and mathematicians take quite seriously when they think carefully about the Fermi paradox. The hypothesis goes essentially like this. The universe is full of intelligent civilizations, perhaps millions of them, but they stay completely silent, never broadcasting, never revealing themselves, because making your presence known across interstellar distances is extraordinarily dangerous. Any civilization advanced enough to receive your signal and travel to your location is also, by definition, advanced enough to be an existential threat to your survival. Resources are limited. Trust is impossible across vast distances and alien psychology. So everyone stays quiet, hiding carefully in the dark forest of space, listening intently but never speaking, never revealing their location. Any civilization that reveals itself clearly, that broadcasts its presence carelessly, gets systematically eliminated by those civilizations that prefer silence and have the capability to enforce it. It's game theory applied to cosmic sociology. Loeb suggests speculatively but seriously that if 3I/Atlas is artificial, if it's a probe or spacecraft from another civilization, it might be operating precisely under these dark forest protocols. Observe carefully but never interact directly. Gather comprehensive data but never reveal yourself clearly. Stay far enough from Earth that you don't trigger active defensive responses or cause panic, but close enough to the inner planets that you can conduct genuinely meaningful surveillance and gather the scientific data your mission requires. It's a reconnaissance mission specifically designed to go unnoticed, to blend in with natural objects as much as possible. The fact that we noticed it anyway, that our detection capabilities have advanced enough to spot it and recognize its anomalies, is either a failure of their stealth technology and operational security, or it's an indication that they don't consider us threatening enough to bother hiding from more carefully. Perhaps we're simply not advanced enough to matter yet, not capable of responding in any way that would concern them. That's where the vast majority of scientists stop taking Loeb seriously at all, where they dismiss him completely. Dark forest scenarios sound fascinating and frightening in science fiction novels, but applying them to real astronomical objects requires assuming things we have absolutely no empirical evidence for. It requires assuming that alien civilizations exist, that they care about us specifically, that they operate according to strategic principles we can understand and predict, and that they're actively watching and studying our solar system right now. That's a tremendous stack of assumptions piled on top of each other with essentially no empirical foundation supporting any of them. But here's what makes Loeb genuinely difficult to dismiss entirely, what keeps serious scientists reading his papers even when they disagree vehemently. He's not just making up dramatic stories for attention. He's not writing science fiction. He's proposing specific, testable, falsifiable hypotheses. If 3I/Atlas is actually a spacecraft operating under dark forest protocols as he suggests, it should behave in very specific, predictable ways as it approaches perihelion over the next 2 weeks. It should not fragment catastrophically under thermal stress the way a natural icy comet would. It should maintain structural integrity and cohesion despite experiencing intense solar radiation and extreme temperature gradients. It should possibly release smaller objects, daughter probes that disperse to multiple destinations throughout the inner solar system. And it should demonstrate active propulsion, accelerating away from the sun faster than gravity alone would predict, proving beyond doubt that it has functioning engines or propulsion systems. All of those predictions can be rigorously tested through careful observation over the next few weeks. If 3I/Atlas fragments like a normal comet breaks apart spectacularly at perihelion, then Loeb is simply wrong and we can all move on with our lives, return to conventional astronomy. If it doesn't fragment, if it does any of the specific things he's predicting based on the artificial hypothesis, then we have an extremely serious problem that demands immediate attention, because at that point the natural explanations become increasingly contrived, increasingly implausible, while the artificial explanation becomes increasingly compelling and difficult to ignore. Loeb has also been discussing publicly and in technical papers what he calls the mothership hypothesis. This idea suggests that 3I/Atlas isn't actually a single monolithic object but rather a carrier vehicle for numerous smaller probes, a mothership design. As it passes through the inner solar system on its carefully planned trajectory, it systematically releases these mini-probes to study multiple targets simultaneously, maximizing scientific return. Each individual probe is small enough to be extremely difficult to detect with current telescopes and tracking systems, but large enough to carry sophisticated sensors, communication equipment, perhaps even sample collection capabilities. They disperse to different planets, gather comprehensive data, then either rendezvous with the mothership for data transfer and retrieval, or continue independently into interstellar space carrying their data home. This isn't pure speculation disconnected from reality. It's based directly on how we ourselves would design an interstellar exploration mission if we had the technology and resources. You absolutely would not send one single massive probe to one single target. That's inefficient, puts all your eggs in one basket, limits your scientific return catastrophically. You would send a mothership design that deploys multiple smaller probes to multiple diverse targets. It's more efficient, more robust against individual failures, dramatically better science return for your investment of resources and energy. If we would design it that way using basic engineering logic, why would we assume aliens would approach it differently? The challenge is detecting those hypothetical mini-probes if they actually exist. Something roughly the size of a refrigerator or smaller, moving on an independent trajectory, would be nearly impossible to spot with current telescopes unless we knew exactly where to look, unless we could predict their trajectories. But Loeb has a specific plan for addressing that challenge. His Galileo project has established observatories in Massachusetts, Pennsylvania, and Nevada, specifically designed and optimized to track anomalous objects in Earth's atmosphere and in near-Earth space. If 3I/Atlas releases anything in our direction, if probes are deployed toward Earth, Galileo project telescopes will be watching carefully with instruments optimized for exactly this kind of detection. November and December are going to be absolutely critical months, not just for 3I/Atlas observations from major facilities, but for what Loeb calls enhanced UAP monitoring, increased vigilance for unidentified anomalous phenomena. He expects, based on his analysis and models, that if there's any connection between 3I/Atlas and the unidentified anomalous phenomena that military pilots keep reporting with increasing frequency, phenomena that Congress is now taking seriously enough to hold hearings about, we should see measurably increased activity during and immediately after perihelion. If the mothership hypothesis is correct, if mini-probes are being systematically deployed to various targets throughout the solar system, some of them might very well enter Earth's atmosphere to gather close-range data on our technological civilization, our atmospheric composition, our biosphere. The Galileo project will be looking specifically for exactly that kind of activity with instruments designed to collect rigorous scientific data rather than grainy phone videos. Critics say this is mission creep, that Loeb is losing scientific rigor. You started with an unusual comet showing some anomalous properties, and now you're predicting alien probe swarms entering Earth's atmosphere. Where's the evidence? Where's the logical connection between an interstellar object and UAPs? But Loeb points out quite reasonably that we shouldn't be looking for evidence of multiple separate, unrelated phenomena. We should be looking for evidence of one single phenomenon manifesting in multiple different ways across multiple domains. If there genuinely is non-human intelligence operating in our solar system right now, conducting scientific observations of us, it wouldn't just announce itself politely and wait for permission. It would conduct comprehensive operations across multiple domains simultaneously. Space-based observations from safe distances, atmospheric surveys to study our weather and climate and atmospheric chemistry, possibly even surface monitoring to understand our technological development and assess potential threats. Connecting those dots, seeing them as parts of one coherent operation, isn't conspiracy thinking or paranoia. It's basic operational analysis of the kind any intelligence agency would do. The scientific community's response to Loeb has evolved in genuinely interesting ways over the past 8 years. In 2017, when he first suggested publicly that Oumuamua might be artificial technology, the response was almost uniformly negative and often personally hostile. Colleagues called him reckless, irresponsible, accused him of damaging the entire field of astronomy, making it harder for serious scientists to be taken seriously. Now, with 3I/Atlas showing even stranger, even more difficult to explain behaviors than Oumuamua ever did, the responses are notably more nuanced and less immediately dismissive. Some researchers still dismiss him entirely, won't engage with his arguments at all, consider him beyond the pale. But others are quietly admitting, usually privately or anonymously, that while they wouldn't personally phrase things the way Loeb does, while they think his language is too strong, they also genuinely don't have good natural explanations for everything they're observing. They're uncomfortable, uncertain, questioning assumptions they previously held with absolute confidence. That shift is genuinely significant. It suggests that even among scientists deeply invested in conventional explanations, scientists whose careers are built on natural astrophysics, the 3I/Atlas data is causing real doubt, creating genuine uncertainty. They're not ready to call it alien technology publicly, they're not willing to risk their careers and reputations on that claim, but they are increasingly ready to admit privately that something genuinely weird is happening and they fundamentally don't understand what. Loeb has been arguing persistently for years that we need to completely flip the burden of proof when it comes to interstellar objects. Instead of automatically assuming everything is natural until proven otherwise beyond any shadow of doubt, we should investigate everything as potentially artificial until we can conclusively, definitively rule that possibility out. That doesn't mean believing every UFO story uncritically. It doesn't mean abandoning scientific rigor or skepticism. It means applying exactly the same level of rigor, the same careful analysis, the same high standards, to the artificial hypothesis that we routinely apply to natural hypotheses. Test both seriously. See which one fits the observational data better. Follow the evidence honestly wherever it leads, even if it leads somewhere uncomfortable. That approach makes many scientists deeply uncomfortable because it feels like giving undeserved credibility to fringe ideas, legitimizing conspiracy thinking. But Loeb argues persuasively that this discomfort is exactly the kind of motivated reasoning that causes catastrophic type 1 errors. We're so afraid of looking foolish by investigating the wrong hypothesis, so concerned about our reputations and careers, that we would rather miss a genuine, civilization-changing discovery than risk being wrong in a way that makes us look gullible. That might be acceptable, might be reasonable risk management in other scientific fields where the stakes are lower. In the search for extraterrestrial intelligence, in questions about whether we're alone in the universe, it's potentially catastrophic. NASA has been notably quiet, cautious in their official statements. They acknowledge the anomalies but emphasize the need for more data, more observations, more certainty before drawing any extraordinary conclusions. But behind closed doors, sources suggest that discussions are happening at the highest levels about what to do if 3I/Atlas doesn't fragment at perihelion, about what it means if the object demonstrates clear evidence of being artificial. The implications are staggering, almost impossible to fully grasp. If 3I/Atlas is confirmed to be alien technology, everything changes instantly. Every assumption we've made about our place in the universe becomes obsolete. We're not alone. We've never been alone. Intelligent life exists beyond Earth, has mastered interstellar travel, and is actively studying our solar system right now. The Fermi paradox, that haunting question of where is everybody, gets answered definitively. They're here, they've been here, and they're watching us. But it raises even more terrifying questions. Why are they here? What do they want? Are their intentions benign, neutral, or hostile? Are we being studied the way we study bacteria in a petri dish, observed with detached scientific curiosity? Or are we being evaluated, assessed as a potential threat or resource? The dark forest hypothesis suggests we should be deeply concerned that any sufficiently advanced civilization capable of interstellar travel might view other civilizations as existential threats to be eliminated before they become dangerous. Loeb has calculated specific windows when we should expect to see activity if the mothership hypothesis is correct. Late November through early December represents optimal timing for probe deployment to Mars and Jupiter based on orbital mechanics and energy requirements. If we see unusual objects, small fast-moving targets that weren't there before, appearing near those planets during that time frame, it would constitute extremely strong evidence that something deliberate and coordinated is happening. The Galileo project is preparing for exactly that scenario. Multiple observation stations are coordinating to provide continuous coverage of critical areas. If probes are released, if objects separate from 3I/Atlas and dispersed to multiple destinations, Galileo project instruments are positioned to detect them and track their trajectories. This isn't passive astronomy anymore. This is active monitoring for potential first contact or potential threat assessment. Think about what humanity faces in the next 40 days. October 29th, perihelion, when 3I/Atlas faces maximum solar radiation and we learn whether it's natural or something else entirely. November and December, when any deployed probes would reach their destinations. By the end of this year, by the time we're celebrating a new beginning in 2026, we might know with certainty whether we share the universe with other intelligences, whether Earth is one civilization among countless others, or whether we remain alone in the vast cosmic dark. The scientific community is fracturing over this, dividing into camps. Some researchers maintain absolute commitment to natural explanations, insisting that no matter how unusual the data appears, there must be some combination of rare but possible natural processes that can account for everything. They're not being unreasonable or closed-minded. They're applying the same rigorous skepticism that has protected science from countless false claims throughout history. Others are quietly, cautiously opening themselves to the possibility that this time might be different, that the accumulation of anomalies might actually represent something genuinely unprecedented. They're not claiming certainty. They're simply saying we should investigate both hypotheses seriously, that dismissing the artificial hypothesis without thorough investigation might be the greatest mistake humanity ever makes. And then there's a third group, smaller but growing, scientists like Sabine Hosenfelder and now a few others willing to speak publicly, who are saying we've already passed the threshold where natural explanations require more elaborate assumptions than artificial ones. They're arguing that Occam's razor, properly applied, might actually favor the hypothesis that seems most extraordinary, because it requires fewer unsupported assumptions than stacking multiple rare natural phenomena together. The next 60 days will test more than just one object's composition and behavior. They'll test whether human civilization, whether science as an institution, can handle a discovery that challenges everything. Can we update our worldview quickly enough? Can we overcome the social and professional pressures that punish scientists for considering uncomfortable possibilities? Can we distinguish between healthy skepticism and willful blindness? Consider what's at stake if we're wrong in either direction. If we dismiss 3I/Atlas as natural and it's actually artificial, we miss the opportunity of a lifetime, perhaps the opportunity of our entire species' existence. We fail to prepare for contact or for threat. We remain ignorant when we could have knowledge. If we investigate seriously and it turns out to be natural after all, what have we lost? Some time, some resources, some embarrassment for scientists who advocated investigation. The asymmetry is overwhelming. This is why Sabine's intervention matters so much, why her breaking ranks with scientific orthodoxy sends such powerful ripples through the community. She's not a UFO enthusiast. She's not someone predisposed to believe in aliens. She's spent her career being the voice of reason, of skepticism, of rigorous thinking. When someone like that says we need to take the possibility seriously, it carries weight that no amount of speculation from UFO researchers ever could. The Columbia sphere that responds to Sanskrit chants, the UAP surviving a Hellfire missile, the Mars biosignatures, the AI achievements, these aren't unrelated curiosities. They're pieces of a larger puzzle that we've been too afraid to assemble. What if consciousness and intelligence are far more common in the universe than we've assumed? What if technological civilizations rise and fall across cosmic timescales, leaving artifacts and probes scattered throughout the galaxy? What if we've been swimming in evidence all along but refused to see it because seeing it would be too frightening, too destabilizing? Ancient civilizations described gods descending from the sky in flying vehicles. We dismissed these accounts as primitive mythology, as pre-scientific people trying to explain natural phenomena they didn't understand. But what if they were describing exactly what they saw? What if visitation has been ongoing for millennia, sporadic but persistent, and we've rationalized away every piece of evidence because accepting it would shatter our comfortable assumptions? The next few weeks might force us to confront that possibility directly, without the comfortable buffer of historical distance. 3I/Atlas is happening now in real time with instruments recording every detail. We can't dismiss it as ancient mythology or unreliable eyewitness testimony. We're watching it unfold with the full power of modern science. And the data keeps getting stranger, keeps pushing us toward conclusions we're desperate to avoid. October 29th is now just days away. Telescopes around the world are positioned, observation schedules locked in, instruments calibrated and ready. Space-based observatories have adjusted their pointing to track 3I/Atlas through perihelion. ESA's JUICE spacecraft has the best view of anyone, unobstructed by Earth's atmosphere, positioned to capture high-resolution data throughout the critical period. Whatever happens, we'll have unprecedented documentation, the clearest view humanity has ever had of an interstellar visitor during its most active phase. If the object fragments, if it breaks apart in a spectacular display of ice and dust sublimating explosively under solar heating, the natural hypothesis is confirmed and Loeb and Sabine will face renewed criticism for crying wolf, for seeing aliens where there were only comets. They'll survive professionally because they hedged appropriately, because they presented their concerns as possibilities requiring investigation rather than certainties, but the stigma will linger. If the object doesn't fragment, if it maintains structural integrity or does something even stranger, demonstrates active maneuvering or releases smaller objects, then everything changes. The conversation shifts instantly from whether we should investigate to how we respond, what we do with the knowledge that we're not alone. The scientific papers are already being written, conditional drafts prepared for either scenario. Some researchers have analyses ready to publish explaining how natural processes could account for survival through perihelion, unusual outgassing patterns that provide structural support, composition models that predict higher tensile strength than typical comets. Others have papers prepared arguing that survival would constitute strong evidence for artificial origin, that natural explanations become increasingly untenable. The media is watching, waiting. The moment perihelion passes, the moment data starts flowing from observatories, journalists will be calling scientists demanding explanations, sound bites, predictions about what it means. The story will dominate news cycles for days, perhaps weeks if the results are ambiguous or extraordinary. And somewhere out there, if 3I/Atlas truly is artificial, if it truly carries intelligence from beyond our world, beings are watching us watch them. They're observing how we react, how we analyze, what conclusions we draw. They're learning about humanity through our response to their presence. Are we thoughtful or reactive? Open-minded or fearful? Unified or fractured? What we do in the next few weeks might determine how they proceed, whether they reveal themselves or remain hidden, whether they judge us ready for contact or too primitive, too dangerous, too unpredictable. The ancient wisdom traditions spoke of great ages, cycles of rise and fall, moments when humanity faces tests that determine our future trajectory. Perhaps we're living through exactly such a moment now, a hinge point where our choices and reactions shape everything that follows. Do we rise to meet the challenge with courage and wisdom, or do we retreat into comfortable denial? I want you to really think about this as you drift off to sleep tonight. Somewhere above you, moving through the darkness of space at over 200,000 kilometers per hour, there's an object that might represent the most important discovery in human history. In just a few days, it reaches its closest point to the sun and we begin getting answers. Those answers might confirm everything we've believed about our cosmic solitude, or they might shatter those beliefs forever. What does it feel like to live through a moment like this? To exist at precisely the time when humanity might confirm we're not alone. Billions of humans lived and died never knowing the answer to that question. You might be among the first to know with certainty. That's extraordinary. That's humbling. That's terrifying and exhilarating simultaneously. Consider the vast cosmos, billions of galaxies, each containing billions of stars, most of those stars harboring planets. The mathematical probabilities suggest that life should be common, that intelligence should arise countless times across those unfathomable distances. Yet until now, we've had no proof, no evidence, just silence and statistics and speculation. That silence might be about to end with the simple confirmation that an object passing through our solar system was designed, built, and sent by minds other than ours. Every generation thinks they live in special times, that their moment is uniquely important. Usually that's just egocentric bias, the human tendency to inflate our own significance. But sometimes, rarely, a generation really does live through genuinely pivotal moments. The invention of agriculture, the development of written language, the scientific revolution, the industrial age, the nuclear era, the information revolution, moments when everything changed, when humanity crossed thresholds that divided before and after into fundamentally different worlds. We might be living through another such threshold right now. The moment when humanity confirms we're not alone, when we transition from a species confined to our ignorance to a species aware of our neighbors, however distant. That changes philosophy, religion, politics, everything. Every human endeavor, every question we've ever asked about meaning and purpose and destiny, gets recontextualized instantly in light of cosmic perspective. Religious traditions will grapple with theological implications. If intelligent life exists elsewhere, were they also created by God? Do they have souls? Did Christ's sacrifice extend to other worlds? Or does each civilization have its own relationship with the divine? These aren't academic questions anymore if we confirm other intelligences exist. They become urgent, pressing matters that faith communities must address. Scientists will face their own crisis of understanding. Our theories and models assume life on Earth represents the only known example, the singular data point from which we extrapolate. Multiple data points change everything, allow us to distinguish universal principles from local accidents, to understand what's inevitable about biology and what's contingent on Earth's specific history. Governments and military establishments will immediately shift to threat assessment mode. If they're here, can they harm us? Do they have weapons? What are their capabilities? Should we attempt communication or maintain silence? The strategic implications are enormous, unprecedented, beyond anything our war colleges and think tanks have seriously prepared for despite decades of science fiction exploring the scenarios. And ordinary people, billions of humans just trying to live their lives, will have to integrate this knowledge into their understanding of reality. The sky is no longer empty. We're being watched, studied, perhaps evaluated. That changes psychology, changes how we see ourselves and our place in existence. Some will embrace it with wonder and excitement. Finally, confirmation that we're part of something larger, that the universe is alive with intelligence and possibility. Others will react with fear, seeing threat and danger in the unknown. Still others will retreat into denial, insisting that no matter what the evidence shows, it must be explainable without invoking aliens because accepting aliens is too destabilizing. But reality doesn't care about our comfort level. If 3i/Atlas is artificial, it's artificial regardless of whether we want to believe it. The truth exists independent of our preferences and fears. Science at its best recognizes this, pursues truth even when truth is uncomfortable, even when truth challenges cherished beliefs. As you lie there in the darkness tonight, as your breathing slows and consciousness begins its nightly drift into sleep, Let your mind wander across these possibilities. Imagine being part of the generation that learns the answer. Imagine waking up to news that confirmation has come, that the data is undeniable, that we're truly not alone. How does that feel? What changes in that moment? How do you integrate that knowledge into your understanding of who you are and what your life means? Or imagine the alternative, that 3I/Atlas fragment spectacularly proves to be nothing more than an unusual comet, and we return to our previous state of cosmic ignorance and solitude. Does that bring relief or disappointment? Are we grateful to avoid the disruption, or sad to miss the opportunity? Either way, the question has been raised now in ways that can't be ignored. Even if 3I/Atlas is natural, we know interstellar objects pass through regularly. We know that some unknown fraction of them could potentially be artificial. We know that our detection capabilities are rapidly improving. This question will come back repeatedly until eventually we get a definitive answer one way or another. The universe is vast beyond human comprehension. Ancient light reaches us from galaxies so distant that they existed when our universe was young, when stars were just beginning to forge the heavy elements that make planets and life possible. Across those distances, across those timescales, how many civilizations have risen? How many achieved technology, reached for the stars, sent out probes to explore and understand? We've sent our own primitive probes beyond the solar system. Pioneer and Voyager spacecraft carrying messages for any intelligence that might find them, gold records with images and sounds of Earth, maps showing our location. We did that decades ago with 1970s technology. What might a civilization 1,000 years more advanced do? 1,000,000 years more advanced? They would fill the galaxy with self-replicating probes, billions of them, an invisible network studying every star system, every planet, cataloging life and intelligence wherever it emerges. They would watch us the way we watch animal populations in wildlife preserves, observing without interfering, gathering data on how we develop. And we would rarely notice because their technology would be so advanced, so far beyond our comprehension, that we'd mistake their artifacts for natural objects unless we looked very carefully. Perhaps that's what 3I/Atlas represents. Not an invasion fleet, not a threat, but a node in an ancient network, a probe sent out millennia ago by a civilization that might not even exist anymore, still functioning according to its original programming, still gathering data and transmitting it to receivers we can't imagine. Perhaps hundreds of such probes have passed through our solar system throughout human history, and we only noticed this one because our technology finally reached the threshold necessary for detection. That possibility is somehow both comforting and deeply unsettling. Comforting because it suggests observation rather than aggression, scientific curiosity rather than hostile intent. Unsettling because it means we're subjects being studied, specimens in someone else's grand research project, lacking agency or control over our own discovery. But that discomfort might be inevitable. Any first contact scenario involves asymmetry unless we happen to encounter a civilization at precisely our technological level, which seems statistically unlikely. More probably, any intelligence we encounter will be vastly more advanced, operating on principles we struggle to understand, making decisions based on considerations we can't fathom. We'll be, briefly, in the position every isolated human culture has faced when contacted by more technologically advanced societies. Uncertain, vulnerable, forced to adapt rapidly to new realities. History shows those encounters usually don't go well for the less advanced culture. Indigenous populations around the world can testify to the trauma of contact, the disruption of traditional ways, the loss of autonomy and identity. But we can't hide forever. The universe is too vast, technology too inexorable in its advance. Eventually, contact happens whether we're ready or not. If you've made it all the way to the end of this incredible journey through one of the most important moments in scientific history, I want to hear from you right now. Drop a comment and tell me, I'm ready for the truth. That's how I'll know you watched until the very end and you're genuinely engaged with what might be the most important story of our lifetime. Hit that like button if you want to see the follow-up video analyzing what actually happens on October 29th. Make sure you're subscribed with notifications on because when that data comes in, when we get answers, you'll want to know immediately. And click on the next video that's appearing on your screen right now. There's so much more to explore about this extraordinary moment in human history. Thank you for taking this journey with me through the mysteries of 3I/Atlas, through the scientific debates and possibilities and profound questions about our place in the universe. The next few weeks will reveal whether this object is just an unusual comet or something that changes everything. Either way, we're living through a moment that future generations will study and remember. Be present for it. Pay attention. Understand what's at stake. And whatever happens, be ready for your worldview to expand in ways you never imagined possible.